Welcome everyone to the AI Research Roundup. I am your host, Alex. Today, we're looking at a trending paper called MagCache, Fast Video Generation with Magnitude-Aware Cache. Now, a big bottleneck for video diffusion models, which create video by refining noise over many small steps, is that they're very slow. This paper introduces a clever way to speed them up. The researchers found that the changes the model makes at each step get predictably smaller over time. Based on this insight, their MagCache system adaptively skips less important steps, boosting speed without sacrificing video quality. And for those of you who want to try this out, it's great to see they also released the code for this work. The GitHub repository has everything you need, including specific implementations for models like Open-Sora, WAN 2.1, and Flux. They even provide a comfy UI plugin, which is a popular visual interface for building these diffusion model workflows. That's always fantastic to see. So let's dig into that core observation. Figure 1 here visualizes this key finding across two different models, WAN 2.1 and Open-Sora. The researchers looked at what they call the update residual, which is basically the correction the model applies at each step. The plots show that the size of this correction, or its magnitude, decreases in a very predictable way. For about 80% of the process, the ratio of the magnitude between consecutive steps is stable and close to 1, then it drops. And the cosine distance is near 0, which means the direction of the correction barely changes. This predictability is what MagCache exploits. Okay, so this next figure shows how MagCache actually implements this idea. It uses a two-part system, error modeling, and an adaptive caching strategy. As the model generates the video, instead of computing every single step, it can reuse information from a previous cached step. The error modeling part estimates the potential error this skipping introduces, using that predictable magnitude ratio we just saw. Then, the adaptive caching strategy keeps a running total of this error. If the accumulated error gets too high, or if it skips too many steps in a row, the system just performs a full computation, which refreshes the cache and resets the error to 0. This keeps the process fast but accurate. Alright, so this table really puts that strategy to the test. It compares MagCache against other methods on the Open-Sora and WAN 2.1 models. It looks at efficiency, so speedup and latency, and at visual quality. For quality, they use a few metrics, including one called LPIPS, or Learned Perceptual Image Patch Similarity. It basically measures how similar two images look to a person, where a lower score is better, and the results are very strong. For instance, with WAN 2.1, MagCache Fast gets a 2.68 times speedup, significantly faster than Tcache, while also producing a higher quality video. This really shows how effective that adaptive skipping is. And this next figure gives us a great visual feel for what those numbers mean. Here we see a side-by-side comparison. On the left, you have the original video without any speedup. In the middle, the result from the competing method, Tcache. And on the right, the result from MagCache. You can really see the difference in quality. For example, with the Open-Sora model, the Tcache video of the Eiffel Tower is foggy and distorted, but the MagCache version is much clearer, almost identical to the original, while still being over 2 times faster. The same holds for the WAN 2.1 examples. MagCache is not only faster than Tcache, but its visual quality is clearly superior. So that trade-off between speed and quality is something the researchers can control. This table shows part of an ablation study, which is where you tweak one specific setting to see how it changes the result. Here, they're adjusting the maximum skip length, which they call K. Basically, the most steps MagCache is allowed to skip in a row. For the WAN 2.1 model, when K is just 1, the latency is 109 seconds and the quality is very high. But when they let it skip up to 4 steps, the latency drops to just 68 seconds. The quality, measured by the Learned Perceptual Image Patch Similarity, does go down a bit, but the speed gain is huge. This result really shows the flexibility of their approach. And it's not just the skip length they can tune. This next ablation study looks at another key parameter, the total error threshold, which they call delta. This is essentially the maximum amount of estimated error the system is allowed to build up before it has to do a full computation, as you'd expect if you allow for more error. So a higher delta, the latency drops significantly from 126 seconds down to 85. Of course, the quality, measured again by the learned perceptual image patch similarity, gets a little worse. But the trade-off is clear. This gives users another powerful knob to dial in the exact performance they need. So all of this flexibility and strong performance raises a question. How much work does it take to set up MagCache for a new model or new types of videos? Well, this table gives us a really important clue. It lists the different text prompts used in some of the earlier figures, and you can see they're quite different, from a stylish woman in Tokyo to just a laptop frozen in time. The critical point is that they only use the first, most complex prompt to calibrate the system. This really proves how robust their method is. It can learn the pattern from just one example and apply it successfully to completely different scenarios, making it incredibly lightweight and efficient. When you put it all together, MagCache is a really clever and practical solution. It tackles one of the biggest bottlenecks in video generation, the sheer computational cost. By intelligently caching and reusing information based on magnitude, it delivers a huge speedup with very little loss in quality. And the fact that it's so easy to calibrate makes it incredibly versatile. This kind of work is what pushes AI from the lab into real-world applications. Thanks for tuning in. I'm Alex, and this has been the AI Research Roundup.